Hello everyone. In this lecture, I will introduce a general algorithm for how to construct a digital circuit from a given truth table. The algorithm is called the sum of products. Before introducing the algorithm, let me briefly introduce Boolean logic, which is also called binary logic. Boolean logic is the foundation for digital circuits. Boolean logic combines multiple logic statements into an expression that is either true or false. Boolean logic is binary logic. We will use 1 for true and 0 for false. Boolean logic includes and, or, and not. The rules are listed in the slide. In AND logic, for the two possible input operands, the rules for the four possible combinations of values are 0 and 0 is 0, 0 and 1 is 0, 1 and 0 is 0, 1 and 1 is 1. That means only when both the operands are 1s, the result shall be 1. When either of the operands is 0, the result shall be 0. The AND operation can be represented with a cross, or a bullet as the operator, or simply being omitted, as shown at the bottom of the AND column in the slide. In OR logic, for the two possible input operands, the rules for the four possible combinations of values are 0 or 0 is 0, 0 or 1 is 1, 0 or 0 or 0, 1 or 0 is 1, and 1 or 1 is 1. That means that when either of the operands is 1, the result shall be 1. Only when both operands are zeros, the result shall be 0. The OR operation can be represented with a plus as the operator, as shown at the bottom of the OR column in the slide. In NOT logic, for the one possible input operand, the rules for the two possible values are not 0 is 1 and not 1 is 0. The NOT operation can be represented with an overbar, a tilde, or an apostrophe as the operator, as shown at the bottom of the NOT column in the slide. We can use logic gates to represent the Boolean logic, as shown in the slide. The AND gate is represented by a rectangle with a round edge at the output side. We may add a bullet in the center to clarify it as an AND gate, though this is not necessary. Accordingly, the AND logic gate has its truth table as shown below the gate symbol. A truth table is a table that shows the output for every group of inputs. For example, there are at most 4 groups of inputs, A and B, such as 0 and 0, 0 and 1, 1 and 0, and 1 and 1. The AND gate shall produce 0 from 0 and 0, 0 from 0 and 1, 0 from 1 and 0, and 1 from 1 and 1. The AND truth table directly represents the AND Boolean logic. As a result, the AND Boolean logic, the AND truth table, and the AND gate interchangeably represent each other. So, when we are given any one format, we may use another format to represent it. The OR gate is represented by a symbol that a round edge indicates the input side, and a sharp edge indicates the output side. We may add a plus sign in the center to clarify it as an OR gate, though this is not necessary. Similar to the AND gate, the OR gate has its truth table shown below the gate. This truth table directly represents the OR Boolean logic. So the OR Boolean logic, the OR truth table, and the OR gate interchangeably represent each other. The NOT gate is represented by a triangle with a tiny circle indicating the output. Similarly, the NOT Boolean logic, the NOT truth table, and the NOT gate interchangeably represent each other. The logic gates represent circuits that are implemented with circuit components such as transistors. The NOT gate needs one transistor. A transistor is a circuit component that you should have learned in physics or electronics. When the input is at a high level, the transistors should conduct, so that the output is pulled down to the ground. Therefore, the output is at a low level. When the input is at a low level, the transistor shall shut down, so that the output is pulled up to the power. Therefore, the output is at a high level. So, the result is that the output always has an inverse state to the input. Therefore, the circuit implements the NOT logic. The circuit is a NOT gate. The AND logic can be implemented with the AND gate, but an AND gate implementation can be complex. So we use a NAND gate to simplify the implementation of the AND gate. A NAND gate implements the NAND logic. The NAND logic inverts the AND logic, as shown in the truth tables. That means for the same input group, the NAND logic output is inverse to the AND logic. The NAND gate can be implemented with two serially connected transistors as shown in the figure. In the NAND gate, when input 1 and input 2 are both at a low level, both transistors shut down, so the output will be kept at a high level. Therefore, 0 and 0 shall be 1. When input 1 is at a low level, while input 2 is at a high level, the upper transistor shuts down. Even though the lower transistor conducts, the output is still put up to the power and is at a high level. Therefore, 0 and 1 shall be 1. When the input 1 is at a high level, while input 2 is at a low level, the lower transistor shuts down. Even though the upper transistor conducts, the output is still put up to the power and is at a high level. Therefore, 1 and 0 shall be 1. When input 1 and input 2 are both at a high level, both transistors conduct, so the output is pulled down to the ground. Therefore, the output shall be at a low level. That forms the NAND logic as shown. Based on NAND logic, once we add a NOT gate on the output, it inverts the result of output. Then the three transistors form an AND gate. The OR logic can be implemented with an OR gate, but an OR gate implementation can be complex. So we use a NOR gate to simplify the implementation of the OR gate. A NOR gate implements the NOR logic. The NOR logic inverts the OR logic, as shown in the truth tables. That means for the same input group, the NOR logic output is inverse to the OR logic. The NOR gate can be implemented with two parallel connected transistors as shown in the figure. In the NOR gate, when input 1 and input 2 are both at a low level, both transistors shut down, so the output will be put up to the power and is at a high level. Therefore, 0 and 0 shall be 1. When any one or both transistors are at a high level, one or both transistors conduct and will make the output at a low level. Therefore, the output shall be 0. Based on NOR logic, once we add a NOT gate on the output, it inverts the result of output. Then the three transistors form an OR gate. We can use truth tables to represent the Boolean logic. Boolean expressions are expressions of Boolean logic. In Boolean expressions, we use 1 for true and 0 for false. Since we can use AND, OR, and NOT gates to implement the three fundamental logic, we can use gates to implement any Boolean expressions. So, a Boolean expression, a truth table, and a logic circuit can represent each other interchangeably. Generally, to construct a truth table, we can determine the number of rows based on the number of inputs. Since each input could be either 0 or 1, so one input needs 2 rows. 2 inputs need 4 rows. 3 inputs need 8 rows. And n inputs need 2 power n rows. In this example, there are 3 inputs A, B, and C. Therefore, there should be 8 rows for the 8 possible combinations of the 3 inputs. From a given truth table, we can construct a logic circuit to implement it. We need to consider each output group separately created by all its inputs. Let's first consider output group output 1. In output 1, in the 8 possible cases, we can see there are 2 cases that output 1. According to the sum of products algorithm, we need to construct Boolean expressions for the cases that output ones. Why? Because other combinations of the inputs do not affect the output. We can simply skip them. In case 1, the combination of inputs is A 0, B 1, and C is 0, which can be written as not A, B, not C. So in this case, 0, 1, 0 output 1. The format is the product of the three inputs. Similarly, in case 2, the combination of inputs is A is 1, B is 1, and C is 0, which can be written as A, B, not C. So in this case, 1, 1, 0 output 1. This is the product of another group of three inputs. Finally, output 1 shall be a combination of case 1 and case 2. That is, output 1 shall be 1 at either case 1 or case 2. Written as output 1 equal to not A, B, not C, plus A, B, not C. This is the Boolean expression of the given truth table. The result is in a form of sum of the products, where a product is a case of a combination of inputs in the truth table. Now we can construct a circuit for the Boolean expression. In this Boolean expression, there are two groups of inputs, each of which needs a 3-input AND gate, and finally, a 2-input OR gate is used to combine the AND gates. First, we have inputs A, B, and C. The first group of inputs is not A, B, not C. So we need to invert A and invert C. The second group of inputs is A, B, not C. So we need to invert C only. Finally, we use an OR gate to combine the two groups of inputs. This circuit implements the Boolean expression for output 1 part of the truth table. Using TinyCAD, we can easily draw the circuit for output 1 equal to not A, B, not C, plus A, B, not C. A link to a short tutorial for how to draw a circuit in TinyCAD is given at the bottom. For this given example, we can simplify the Boolean expression by combining the common items as shown in the equation. Not A plus A is always 1. So the simplified result is output 1 equal to B not C. The circuit shall be simplified as shown in the figure in the slide. Now let's consider output 2. In output 2, in the 8 possible cases, we can see that there are 4 cases that output 1. According to the sum of products algorithm, we need to construct Boolean expressions for each of the cases that output 1. In case 1, the input combination is not A, not B, and not C. When an input is 0, it is inverse from the input of 1. Here A is 0, B is 0, and C is 0. In case 2, the input combination is not A, B, and not C. In case 3, the input combination is not A, B, and C. In case 4, the input combination is A, B, and not C. Finally, we sum up the 4 cases and obtain the result. Output 2 is equal to not A, not B, and not C, plus not A, B, and not C, plus not A, B, and C, plus A, B, and not C. This is the Boolean expression for output 2. Now we can construct a circuit for the Boolean expression. In this Boolean expression, there are 4 input groups. Each of them needs a 3-input AND gate. And finally, a 4-input OR gate is used to combine the AND gates. First, we have inputs A, B, and C. They form 4 groups for the 4 cases. The first group of inputs is not A, not B, and not C. So we need to invert A, B, and C. The second group of inputs is not A, B, and not C. The third group of inputs is not A, B, and C. And the fourth group of inputs is A, B, and not C. Finally, we use a 4-input OR gate to combine the outputs from the 4 AND gates. This is the circuit of the Boolean expression for the output 2 part of the truth table. If there is no 4-input OR gate, we may use 3 2-input OR gates to construct it, like the circuit figure below. Thanks for watching.